The cycles of a four-stroke internal combustion engine are intake, where the intake valve opens, allowing the fuel-air mixture into the cylinder; compression, where the intake and exhaust valves close and the mixture is compressed, and, due to compression, is heated; ignition expansion, where the mixture is ignited and the hot gases expand; and finally, exhaust, where the exhaust valve opens and the combusted gases are expelled from the cylinder. The tremendous kinetic energy possessed by the expanding combustion gases provides the mechanical energy to drive pistons up and down. This up and down motion turns a crankshaft to produce rotary motion. The heat, thermal energy, is so great from an internal combustion engine that a cooling system has to be used to remove thermal energy from the engine. A pump moves the cooler fluid from the bottom of the radiator, denoted by a blue color. As the fluid flows through the hot engine, heat is transferred to the fluid and it gets hot, denoted by a red color. This hot fluid then flows into the top of the radiator, where the fluid is cooled by air, which is heated as it passes through the radiator cooling fins. Pistons and valves work together to provide energy to the crankshaft of an engine. The crankshaft drives a transmission that provides power to the wheels. It also rotates pulleys and belts to turn an alternator to generate electrical power for the vehicle, a water pump for the cooling system, and other accessories such as air conditioning and power steering. Mechanical energy is provided to the wheels from the engine through a transmission, drive shafts, and/or axle shafts. Each step along the way consumes energy with frictional, thermal, and gear mechanical losses. Once a vehicle is in motion, friction of the tires with the road and flexing of the tires themselves create thermal energy losses. Also, air resistance or drag adds to the thermal energy losses of the vehicle. When the brakes are applied, the vehicle's mechanical energy is transformed into thermal energy, where the brake pads press against the brake rotors.
Yes! Eureka! Oh, hello there. I was just doing some analysis on Ford Motor Company's exciting hybrid electric vehicle, the Prodigy. If my calculations are correct, the Prodigy can go from London to Moscow for less than... How much? This is unbelievable. Well, I guess there's only one way to find out. Remember, the true answers in life are not always discovered by taking the most obvious route. To demonstrate Prodigy's efficient hybrid design, we'll travel from town to town, through traffic, across Europe, on A roads and back roads, to show how Prodigy converts coasting and stopping into useful energy. This is going to be exciting, because the Prodigy is an extraordinary hybrid electric vehicle. It's built with highly efficient drivetrain components, like a lightweight 1.2-liter aluminum compression ignition engine, an integral starter alternator, an advanced high-power battery, and an automatically shifted manual transmission. From the driver's perspective, the Prodigy drives just like a conventional car, with some important advantages, like very low emissions, and, as you can see, outstanding fuel economy. Remarkable, isn't it? London to Brussels for under 15 marks. Pretty cool, eh? That's the kind of efficiency you get with Prodigy's high-tech hybrid design. The lightweight compression ignition engine powers the Prodigy only when you step on the accelerator. When coasting, engine power is not required, and the fuel is shut off. And as you decelerate or apply the brakes, the starter alternator converts Prodigy's forward motion into energy that is stored in the battery. So right now, Prodigy's not using any fuel at all. In fact, it's actually generating energy. That's more than economical. It's phenomenal. Now, as the Prodigy slows to a stop, the engine stops and the fuel remains off. That's how Prodigy goes so far, so efficiently. Wow! Less than 31 marks from London to Frankfurt. That's impressive. I spend more than that for a haircut. We saw how Prodigy's fuel shuts off to save energy during deceleration and how the starter alternator generates energy. Now, when it's time to accelerate, stepping on the gas causes the starter alternator to start the engine. And without hesitation, you're on your way, all within a fraction of a second. Actually, 0.2 of a second, like that. But who's counting? So, the same starter alternator used to convert Prodigy's rolling motion into electric energy also starts the engine and provides extra boost when more power is required. Along with its efficient powertrain, Prodigy's lightweight design, which includes an aluminum body that meets all required safety standards, means it takes less energy to get rolling, and Prodigy's highly aerodynamic styling and special tires mean that it takes less energy to keep rolling. Speaking of rolling, we've traveled a long way for very little money, thanks to Ford's innovative approach to building a technically advanced vehicle that's more fuel efficient and more environmentally friendly than vehicles most of us drive today. Ford's next challenge is to make it as affordable as the cars we drive today. The key is to use fuel only when it's needed, and even then use as little as possible. That's the Ford Prodigy, a car so efficient we can travel a distance like London to Moscow for under 112 marks. Now, I'm no Einstein, but relatively speaking, I'd say the Ford Prodigy just might change the way we see the world and help make our planet a cleaner place to live.
There are 7 major fuel economy technologies being used by engineers in developing the Prodigy. They are reduction of mass, smaller engine, instant on-off capabilities, regenerative braking, advanced transmission technology, better aerodynamic design, reducing rolling resistance of tires. Engineering design number 1. The reduction of mass. The energy needed to propel an object at a given velocity is directly proportional to its mass. Decreasing the mass by 30% leads to a 30% decrease in the amount of kinetic energy. Prodigy's mass is 30% less than today's comparable vehicles. Less mass means less energy is needed to provide the vehicle with the same velocity. Engineering design number 2, a smaller engine. With lower energy requirements because of lower mass and other fuel economy designs, a smaller engine can be used. A 1.2-liter diesel engine is 1/3 less than the size of today's average car engine. A smaller engine uses less chemical energy to operate. Engineering design number 3. Instant on-off capabilities. There's no reason for having the engine operate while waiting at a traffic light, stuck in traffic, coming to a stop, or coasting down a hill. Sensing these conditions, the Prodigy shuts off its engine. This results in a substantial saving of the chemical energy stored in the fuel tank. With chemical energy stored in the batteries, the engine can be started instantly when needed. Engineering design number 4, regenerative braking. Today's braking systems transform 100% of the vehicle's kinetic energy into thermal energy when the brakes are applied. Prodigy has 2 ways to stop the car. The first is to create friction, which changes the mechanical energy to thermal energy, much like brake pads on a bicycle that press against the wheel. The second way to stop the car is to make the rotating wheels turn a generator that makes electricity. The electricity can be saved as chemical energy in a battery for later use. Typically, about 10% of the mechanical energy is stored in the battery during this process called regenerative braking. The electrical energy is then stored as chemical energy inside the high-power batteries located in the wheel well in the boot. This stored power may be needed to start the engine many times during a trip. The stored electrochemical energy in the batteries may also be required to produce electrical energy when more power is needed by the driver. Engineering design number 5. Advanced transmission technology. Newton's first law of motion tells us that a body at rest will remain at rest until it is acted upon by an outside force. To overcome matter's desire to stay at rest, the vehicle's transmission allows the car to change from rest to slow, to moderate, to fast. These gear changes are accomplished by having the driver change gears manually or by having it done automatically. Some drivers prefer an automatic transmission to a manual transmission. An automatic is simply more convenient, which for some outweighs its lower efficiency. The driver's decision on when to shift gears can affect the amount of energy transferred into unwanted thermal energy. Prodigy has a manual transmission that is shifted by a machine at the most efficient time. This gear-shifting robot reduces thermal energy transfer and increases fuel economy. Engineering design number 6. Better aerodynamic design. Of the 15 units of mechanical energy possessed by the wheels of today's car, 11 units are transferred into thermal energy as a result of tire friction with the road and air resistance. Prodigy's better aerodynamic design reduces air resistance and the mechanical transfer of energy into heat. This results in higher fuel economy. Engineering design number 7. Reducing rolling resistance of tires. Reducing rolling resistance of tires with the road while maintaining safety is a task for engineers. This reduction is primarily achieved by manufacturing a lighter automobile. Less weight means less force between the tires and the road. Also, there is less flexing of tire materials, which causes the production of thermal energy. Tire pressure, design, and composition can also reduce the transfer of motion into thermal energy. Advanced technology and innovative engineering designs will result in concept cars with almost 3 times the fuel economy of today's comparable passenger vehicle. This will be accomplished by managing the use of chemical and mechanical energy and its transformation into thermal energy. As these technologies are proved to be durable, reliable, and affordable, they will be put into production. Some already have.
Hi, my name's Charlotte. I know you've just been learning about the Prodigy and probably still have some questions. I'll be asking Burkhard Schmidt some of those questions. Welcome, Burkhard. Thank you for joining us today.
Thank you for inviting me into your classroom.
With lightweight materials, do you think this car will last as long as today's cars?
Oh, definitely. Our engineers use computers to simulate and analyze all aspects of Ford designs. In the next step, we take early prototype vehicles and accumulate thousands of miles on our test tracks. Our goal for any new design is to meet or exceed its predecessor.
The Prodigy shuts off the engine when the car is stopped. How do you know it will start again when you press the gas pedal?
The engine has electronic ignition and electronic fuel injection, and both are known to be very reliable. Also, we have long-term experience in designing engines to last 150,000 miles and more. Then we take them to our test labs and proving grounds to test them under extreme temperature and humidity conditions.
Will the starting and stopping cause the engine to wear out sooner? And will we be able to feel this starting and stopping when we're driving in the car?
First of all, it will not affect engine life. Second, a power flow display in the instrument panel will tell the driver the flow of power in the car and when the engine is on or off.
And if the car uses diesel, will the environment still benefit?
Oh yes, there will be a benefit for the environment. The energy content of a given volume of diesel is higher than that of petrol. This is one of the reasons why diesel vehicles in general show lower fuel consumptions. So with diesel, you produce less greenhouse gases, and this is good for the environment.
When will the people be able to buy the Prodigy?
Just like any other experimental vehicles, Prodigy has hundreds of new components in it. And they all have to meet internal criteria for reliability, durability, and costs. Some of the lightweight materials, such as aluminium or plastic, are well known and are already in use on our current production vehicles. Others need further development. With all the new technologies in this concept car, it will certainly take another 5 to 10 years to make it available for the customer.
Well, thank you, Burkhard, for joining us today. I hope I'll be able to drive a Prodigy in the future.